Look at the gold on your hand. Cold, heavy, permanent. It has held its shine for years, and it will outlast you, your children, and every empire yet to rise. But here is a question almost no one asks. Where does gold actually come from? And why is it so rare that nations have gone to war for it? The answer is not in any mine. It is not on this planet at all. Every atom of gold you have ever touched was forged in a catastrophe so violent it briefly outshone entire galaxies. The head-on collision of two dead stars. And in 2017, for the first time in history, humanity watched one happen. To understand gold, forget the vault and the crown. Think instead about where atoms are made. Almost everything around you was assembled inside stars. The calcium in your bones, the oxygen in your breath, the iron in your blood. All of it was cooked in stellar furnaces and scattered when those stars died. You are, quite literally, walking stardust. Inside a star, hydrogen fuses into helium, helium into carbon and oxygen, and on up a ladder. Each step building a heavier element, each step releasing energy. This is how a star shines. But the ladder has a top rung, and its name is iron. Fuse anything lighter than iron, and you get energy out. Try to fuse iron itself, and the process turns greedy. It takes more energy than it gives. For a star, iron is ash. The furnace that built every element up to that point simply cannot go any further. And gold sits far, far beyond iron on the periodic table. So the ordinary life of an ordinary star can never make it. To forge gold, the universe needs something extraordinary. For centuries, alchemists chased a single impossible dream: to turn common metal into gold. Kings funded them. Some spent fortunes. A few may even have believed they were close. They failed, every one of them. Gold cannot be made by any chemistry. No mixture, no furnace on Earth even comes close. To build gold, you must rearrange the heart of the atom itself, and that takes energies no laboratory on this planet can reach. The alchemists were not foolish. They were simply born on the wrong world. The only alchemist that has ever succeeded is the cosmos, and its crucible is the death of stars. When a massive star finally chokes on its iron core, it collapses and rebounds in a titanic explosion, a supernova. For decades, we assumed this blast was the cosmic gold mine. But a supernova, for all its fury, struggles to explain the sheer quantity of gold, platinum, and uranium scattered across the cosmos. Simulations hinted that ordinary supernovae simply could not brew heavy elements fast enough or in large enough amounts to fill the universe with the gold we actually find. Something was missing from the story. The clue lay in what a dying star leaves behind. When its outer layers are blown away, the crushed core can survive, an object so dense it defies imagination. Not a black hole, but its stranger cousin, a neutron star. Take the mass of our sun. Now crush it into a sphere the size of a city, barely 20 kilometers across. That is a neutron star. The compression is so extreme that atoms themselves are shattered. Electrons are crushed into protons, and what remains is a single, colossal nucleus of almost pure neutrons. A sugar cube of this material would weigh about as much as a mountain, 1 billion tons. Its surface gravity is billions of times stronger than Earth's. The pressure at its heart is beyond anything else in the known cosmos. Many neutron stars spin hundreds of times a second, sweeping the sky with beams of radiation like a lighthouse. Its interior is the densest matter that can exist without collapsing into a black hole. A neutron star is, in every sense, a stellar corpse. A star that died but did not quite disappear. And sometimes these corpses come in pairs. Across the galaxy, many stars are born in twos, orbiting a shared center of gravity. When both are massive enough, both can end as neutron stars. Two dead cores, locked in a slow, silent dance. But that dance cannot last forever. As Einstein predicted a century ago, two masses whirling around each other stir ripples in the fabric of space itself. Gravitational waves. Each ripple carries away a sliver of energy, and with every orbit, the two stars edge a little closer together. We knew this was real long before we could ever see it. In 1974, astronomers Russell Hulse and Joseph Taylor found a pair of dead stars spiraling inward at exactly the rate Einstein's equations demanded, work that later won the Nobel Prize. It was the first hard proof that gravitational waves were more than a line in Einstein's mathematics. For hundreds of millions of years, the two neutron stars circle each other, closer, faster, until, in the final seconds, they are whirling around one another hundreds of times every second, and the end arrives in an instant. In that last moment, the two neutron stars touch and merge. For a fraction of a second, the most extreme laboratory in the universe blazes into being. Temperatures soar into the billions of degrees. A vast amount of neutron-rich matter is torn from the dying stars and hurled outward at nearly a tenth the speed of light. And here is the secret. This debris is drowning in free neutrons, the one ingredient needed to climb past iron. Atomic nuclei caught in the storm capture those neutrons faster than they can decay, one, two, dozens at a time. In seconds, they race up the periodic table, building heavier and heavier elements. Physicists call it the R process, the rapid capture of neutrons. This is the forge. In that brief, blinding chaos, the collision manufactures the universe's heaviest treasures: platinum, uranium, and gold, and not a trickle. Estimates suggest a single merger can produce gold amounting to several times the entire mass of the Earth. The wreckage of the merger does not simply cool and go dark. The freshly made heavy elements are radioactive, and as they decay, they pour out heat. That heat sets the expanding cloud of debris aglow in a flash astronomers call a kilonova. For a few days, it can shine thousands of times brighter than an ordinary stellar outburst, a beacon announcing that new gold has just been made. For decades, astronomers had suspected these events existed. Now they could finally watch one unfold. Then over a week or two, it fades. But the fading light carries a message, the chemical signature of the elements born in the blast. For a long time, this was a beautiful theory with no eyewitness. Then on the 17th of August, 2017, the eyewitness arrived. Detectors in the United States and Italy, LIGO and Virgo, felt a tremor in space-time lasting about 100 seconds. It was the unmistakable chirp of two neutron stars spiraling to their death, around 130 million light-years away. Less than 2 seconds later, orbiting telescopes caught a burst of gamma rays from the very same patch of sky. Word went out, and within hours, dozens of observatories around the world swung toward that single point in the dark. It became the most studied explosion in the history of astronomy. They watched a new star glow and fade in a distant galaxy, exactly as a kilonova was predicted to behave. It was the first time we had ever observed a single cosmic event in both gravitational waves and light. And in that fading glow, spread across the spectrum, was the fingerprint of freshly forged heavy elements. We had, at last, caught the universe in the act of making gold. Now follow that gold home. The elements forged in such a collision do not stay put. They are scattered across light years, seeding enormous clouds of gas and dust with heavy atoms. Over spans of time that dwarf all of human history, one such enriched cloud drifted, collapsed, and, about 4.5 billion years ago, became our sun, our planets, and everything upon them. Much of that gold sank deep into the molten young Earth, down toward the core, but some stayed within reach of the crust, and eventually within reach of us. The gold humans have ever mined, melted end to end, would barely fill a few swimming pools, the scattered inheritance of ancient stellar deaths. So the ring on your finger is not merely old. It is older than the ground you are standing on. It rode a collapsing cloud, survived the furnace of a forming planet, and waited in the rock for someone to dig it up. Each of its atoms outlived the death of two stars, the birth of a solar system, and billions of years of restless geology. And because gold does not rust, tarnish, or decay, it is, atom for atom, the very same gold that was born in that ancient collision. Unchanged, effectively eternal. We prize gold for its shine and its rarity, and we are right to. It is rare because the universe makes it only in its most violent moments, in the collision of stars that had already died once. There is no factory, no mine deep enough, no reaction we can light on Earth that will ever make more of it from nothing. The next time you see it, a ring, a coin, a thin gold thread inside a circuit board, remember what you are really holding. Not treasure dug from the ground, but ash from a cosmic fire, older than the Earth, carried across 100 million light years, to rest at last in the palm of your hand. The stars, it seems, left us a little something to remember them by.